The Newport News Shipbuilding and Drydock Company's plant at Newport News, Virginia, is the largest private shipyard in the country. Covering an area of 225 acres, it contains every modern facility for the construction of both merchant and naval vessels. Ways can accommodate ships up to 1,000 feet in length. Piers and dry docks are adequate for all types of hull and engine repairs, while complete shop facilities are available for each of the many trades. On April 7th, 1949, the contract to build the SS United States is signed by officials of the United States Lines, for whom the vessel is to be constructed, by the United States Maritime Commission, and by the builders of the vessel, the Newport News Shipbuilding and Drydock Company. This huge liner, costing approximately $72 million, will be the pride of the American merchant marine. On the dark, drizzly morning of February 8, 1950, 10 months from the date of contract, the first section of assembled flat and vertical keel is set in position on the blocks. This is quickly followed by single plates laid both forward and aft of the assembled section. The 10-month interval from contract to keel laying is required for progress of the design, as well as the procurement and fabrication of the material. 90% of the 16,000 tons of structural steel is assembled on platens. This platen, adjacent to the shipway, has an area of 70,000 square feet, served by 3 25-ton gantry cranes. The subassembly method of construction has several definite advantages. The working area is greatly increased. Facilities for handling material are nearly doubled. And on welded construction, it allows a maximum of downhand welding. In addition to the gantry cranes, the platens can also be serviced by 3 of the shipway cranes, which are capable of handling assemblies directly to the ship without intermediate handling. Practically every piece of steel on this ship is subassembled, with exception of the shell plating. Here, a wing section of inner bottom is being installed. Piping is also installed in the assemblies, where ample space permits the handling of odd shapes and long lengths of pipe. Hangers can be easily fitted, which otherwise might be in inaccessible places. The United States was built in a submerged shipway, really a huge dry dock, 960 feet long, 128 feet wide, and 35 feet below sea level. Here are the first operations in the assembly of a section of deck. When the material has arrived at the platen, each individual plate is located in its proper position in an area previously laid off with the necessary reference lines. Plates are first trimmed to proper size. This is done with a radiograph cutting machine. While extra material is left on the overall size, the joints between the plates are cut neat. Quarter-inch plating is cut square, and the bevel for welding chipped by hand. On heavier plating, either a single or double bevel may be burned with this versatile machine, which may be set to cut at any angle. The burned bevel can then be welded without further preparation. After the butts and seams have been prepared, fitted up, and tack welded, the plating is ready for welding. Half-inch and lighter plating is usually welded by manual electric arc. On thicker plating, joints may be burned square and welded with an automatic submerged arc welding machine, which travels on a portable track set parallel with the joint. Once the track is properly aligned, the electrode feed, the current, and the speed of travel are all automatic and depend upon the thickness of the plating. After cooling, the flux, which prevents oxidation of the weld, is removed and salvaged for subsequent use. The plating, welded with the top side up, is turned over for final welding and the addition of the underside structural members. While this is actually a deck section, the same procedure is used on other assemblies which can be done in the flat position. The inverted section of deck, after being lined off for beams and girders, has temporary erection clips tack welded to the plates. These clips provide support for the members until the entire unit is ready for welding. The final structure is completely welded in a downhand position. Once checked for the installation of all minor clips and brackets, it can be turned back to its normal position, have lifting pads fitted for horizontal handling, and then be sent to the ship or to storage until the ship is ready for it. One of the major features in the design of the United States is weight saving. Every attempt has been made to produce the required strength with the least possible weight. Frequently, stiffeners used are serrated on a machine which cuts two 10-inch T-bars from a single 18-inch I-beam. In many cases, a substantial saving in weight results from ordering standard rolled I-beams and burning off the flanges to form T-bars. The strength of the stiffener obtained is adequate and lighter than a standard rolled T-section. Work on the ship progresses, building up the midship portion first, then filling in the stern and bow sections. As soon as the structural work is cleaned up in the inner bottom and holds, these spaces are promptly turned over to the outfitting trades so that installation of machinery, ventilation, electrical, and piping material can be started. Meanwhile, erection continues to the point where our completed section of deck, measuring 20 by 30 feet, goes aboard the ship. Notice the predominant yellow color of the rust. This is because the plating has been pickled to remove the mill scale and provide a good bond for the priming coat of paint. In the 4 months since the keel was laid, the ship has grown amidships to the main deck, but the stern has just been completed sufficiently far aft to receive the spectacle frames, which support the outboard ends of the shafting. These spectacle frames, usually referred to as hull castings, are actually weldments composed of both castings and structural steel. After the welding is done, the unit is lowered into a huge oven and heated to 1100 degrees Fahrenheit to remove the residual stresses due to the welding operation. The arm is made of cast steel, while the barrel through which the shaft will pass is rolled up from steel plate and fitted with internal cast steel rings. The steel structure welded on top of the palm provides the connection to the ship. The 60-ton weldment is finally cleaned up on the ground and then rigged for installation. There are 4 such weldments, 1 for each shaft. Although usually designated as spectacle frames, it's only the aftermost pair that butt on the center line and show a marked resemblance to a pair of spectacles. Following the installation of the spectacle frame is the stern frame, the largest and heaviest weldment on the ship. A specially fitted car is required to move it from the stress-relieving oven to the pier, where it's loaded on a barge for transport to the shipway. Composed of a massive steel casting, rough bored for the rudder stock, it also has the connecting structure welded to it. In order to handle this 240,000-pound lift from the barge to the shipway, an equalizer is rigged between the 75 and a 25-ton crane. The installation of this last major weldment allows the remaining structure to be continued to the extreme after end of the ship. Preference is customarily given to the stern portion of the vessel, because not until these major weldments have been set and the surrounding structure completed can work start on running the line for the shafting. About a month after the stern weldments have been installed, the forward end is ready for the forefoot. While the bow is made up of 4 separate lifts, the lower assembly you see here is probably the most interesting. Composed of 3 individual assemblies, it is built like the deck, upside down. The 3 units, stacked one upon the other, are welded together, complete with shell plating. In this condition, the weight is over crane capacity, so it is cut vertically and shipped in 2 separate pieces. The turning over operation requires careful rigging, the use of 2 or 3 cranes and equalizers, and sometimes a locomotive crane. In handling capacity lifts such as these, where 2 or more cranes are involved, the coordination between the ground crew and the crane operators, and between the operators themselves, must be timed perfectly, as it is essential that the lift hang vertically from each boom at all times. The installation of the assembly you see done here in 45 seconds actually takes several hours from the time rigging is started until it is properly shored up and can be turned loose from the crane. In the development of such a ship, there is considerable research and experimental work necessary to complete the design. Here is a model of the ship's bow housing the 3 anchors. It is built from a preliminary drawing and used to determine the exact angle and shape of the hawse pipes. By trial and error, they are altered until the anchors house satisfactorily, regardless of their position when first coming in contact with the hull. The final design is then taken directly from the model. On most vessels, the port and starboard anchors are rigged for service, while the spare anchor is stowed on deck. Here, all three anchors are rigged, the bow and the starboard anchor being in service, leaving the port anchor for emergency purposes. Note that the side anchors are recessed to prevent heavy seas from loosening them, as well as to minimize the spray. During the construction period, work continues in the shops. Patterns and castings must be made, while fabrication of all sorts of material must be completed. After finishing touches are put on the pattern for the starboard hawse pipe, it will go to the foundry, so the castings will be ready when needed on the ship. The structure aft has now progressed to the point where the aftermost stern sections can be erected. This last piece, overhanging the shipway gate, is to the height of the upper deck. Staging, supplemented by stairways, ramps, and elevators, provides access from the top of the hull to the floor of the shipway, 43 feet below ground level. While the stern is being welded preparatory to boring out the stern tubes, the shafting is machined in the shop. Received from the mill, rough turned and bored, the only remaining work is the final lathe work, plugging the bore and preparing holes for the coupling bolts. All shafting is hollow bored to save weight. Although hollow shafting is somewhat larger than equivalent solid shaft, the same strength can be obtained with a considerably lighter section. The boilers are the first major item of machinery to be installed and must go in at an early date so that the decks over them can be closed up to permit continuation of the steel structure. There are 8 boilers, the largest marine boilers ever built in the United States. Classed as bent tube 2-furnace boilers, they are partially assembled in the shop and when completed will be fully encased. One of the boilers for the vessel is finished ahead of the installation schedule so that it can be shipped to the Naval Boiler and Turbine Laboratory where extensive full power tests will be made. Complete with casing and auxiliaries, its enormous size and weight of 246,000 pounds necessitates the shipment by barge rather than by rail. The main machinery and most of the auxiliaries are likewise installed along with the structural work. There are 4 units, one for each shaft, consisting of turbines and reduction gears of the most advanced design. They can be operated as individual plants to provide protection against total loss of propulsion power in the event of damage. Turbines of the high-speed type are driven by superheated steam at a pressure and a temperature well above the usual marine practice. This necessitates the use of strong alloy steel in their construction. Here is the swimming pool, in reality a big box, 28 feet long, 20 feet wide, and 8 feet deep. Built of Monel-clad steel to resist corrosion, it's much lighter and less susceptible to damage than the customary tiled pool. The blue color is a temporary plastic coating protecting the bright Monel surface. The lined appearance is caused by the removal of the coating where stiffeners are to be welded on the reverse side. The pool is located about 3/4 of the way aft and 5 decks below the promenade deck. The steel work up to and including the promenade deck nears completion as the last section of bow is moved to the ship. The hole on the center line is for the hawse pipe mounted in the stem, the forward end of which projects well over the inboard end of the 960-foot shipway. Above the promenade deck, most of the superstructure will be aluminum. The only steel used will be for the transverse strength members and the forward ends of the houses. Aluminum, weighing only 1/3 as much as steel, not only improves the stability of the vessel, but will make the United States the lightest ship for its size ever built. Over 2,000 tons of aluminum are used in its construction. The aluminum is received with a natural finish, given a special treatment, painted with zinc chromate, and then stored until ordered here to the layoff shed. Wooden templates are built from full-sized lines laid down in the mold loft. They're made for the majority of the 183,000 individual pieces that fit together to form the structure. Here, the template is clamped to an aluminum plate so the information for punching, cutting, or shaping can be transferred. Center punch marks are ringed with chalk for easy identification. Its official designation, stenciled on the plate, identifies it with the drawing from which it was made. After checking, it will be sent to the fabricating shop. While the fabrication of aluminum generally is similar to steel, there are a few practices that differ greatly. The punching operation you see here is identical. The holes are punched undersides. The riveted aluminum results in considerably more punching, since equivalent steel structure normally would be all welded. Care must be taken in the handling of aluminum, as it mars easily, making dents and buckles difficult to remove and preserve the fair surface. The boundaries of large aluminum plates laid off to the full size of the material are planed square to the line. Odd-shaped plates, which do not utilize the entire plate area, are sawn to shape. Whereas with steel, such operations would normally be accomplished by burning. Alterations are far more difficult to make on aluminum. Steel burns readily, but large holes in aluminum have to be chipped out by hand. A butt joint in aluminum must be backed up with a strap and riveted if the flush surface is to be maintained. Aluminum also is subassembled. Instead of being done on a low solid platen, the assembly of aluminum flatwork is done on an open skid, which permits access underneath for bolting and riveting. The material, including the transverse steel structure, is first bolted together. This bolting is only temporary and ensures the proper lining up of the section. The sub-punched holes are then drilled to size instead of being reamed, as they normally would be on riveted steel type of construction. After drilling, the holes are countersunk on one side to provide for flush surfaces, and the material is finally bolted up tight preparatory to riveting. Notice that the holding on tool on the underside of the plates can be easily handled and is supported rigidly from the ground. The aluminum rivets are driven cold. They're delivered to the assembly areas in heat-insulated containers, because the special alloy from which they're made requires that after heat treating and quenching, they be kept at sub-zero temperature until driven. At ordinary temperatures, the rivets would soon harden, so that driving would be difficult. Driven cold in a soft condition, the working of the metal, together with the natural aging at outside temperature, will produce the design strength. The driving operation is fast, since it's not necessary to stop and chip each individual point when driven, nor to go back and harden up the point as on a steel rivet. There are nearly 1.25 million aluminum rivets on the United States, and if driven at an average rate of 1.5 a minute, it would take one gang 6 years to complete the riveting. Aluminum assemblies are erected on the ship and prepared for riveting. In general, after riveting, all exterior joints are caught, just as they would be in steel. In ships of this size, expansion joints are sometimes fitted in the superstructure to limit the excessive stresses produced when the ship is in a seaway. By using aluminum, having a modulus of elasticity only 1/3 that of steel, these high stresses are greatly reduced without the use of expansion joints. The launching day draws near, but not until the last piece of structure and the stacks have been added does the United States assume her full beauty. Here is a model of the vessel in a wind tunnel, being subjected to various wind velocities while smoke is piped to the stacks. The flow is observed as the wind and the exit velocity of the smoke are varied. It's essential for passenger comfort that the exhaust gases have sufficient velocity to prevent the soot from being caught and drawn down on deck by the eddies formed by the stack. The two stacks, measuring over 60 feet long and 55 feet high, are the largest stacks ever constructed. Built with an aluminum outer casing, they both have an inner casing and smoke pipe of steel, which connects to the uptakes from the boilers. These smoke pipes are relatively small, allowing the majority of the space between the casings for ductwork, ventilation fans, and even one of the emergency diesel generators. The use of aluminum for the sampans presents a difficult problem, because most of the plating required shape in 2 directions. With steel, this double curvature is easily obtained by heating the plates and pressing them to form. With aluminum, which cannot be heated, it is necessary to make a suitably curved die and cold work the plates to shape in a hydraulic press. Although we normally think of aluminum as being a light material, The stack is so huge that the top half has to be left loose and installed separately to come within crane capacity. Since handling the upper section requires the use of all shipway cranes, the work is done during off-shift hours so that crane service to the ship is not interrupted. The big crane places the stack on deck. Then, shortly after sunrise, it's rigged for handling by the 4 small cranes, using equalizers and the 10-ton hooks to place it atop the lower section. The 10-ton hooks, located at the extreme ends of the booms, must be used to get enough clearance, since the top of the stack is nearly 180 feet above the floor of the shipway. This is the radar mast, the only mast on the ship, and the last large assembly to go aboard. Built of aluminum, complete with platforms, ladders, and railings, its height is such that line of sight is not obstructed in any direction. Outfitting material closely follows the completion of the structural work. Here, aluminum gravity-type davits are being lined up and tied into the vessel's structure. Although all steel and aluminum structure is installed at the time of launching, the vessel as a whole is only 65% done, while the outfitting and machinery trades are but 45% completed. When the tail shafts have been installed, the vessel is ready for her 4 propellers. After machining, each propeller is rotated in a machine which records any unbalance. From the graph and the location of known weights, engineers calculate the amount of weight to be removed to bring the balance within acceptable limits. The tips of the blades are relatively sharp. They're chipped and ground to a 32nd inch radius and have to be protected against damage while handling. The United States is fitted with 2 4-blade wheels on the outboard shafts and 2 5-blade wheels on the inboard. This arrangement is used to avoid vibration. Completion of the work on the propellers and the shipping of the rudder completes the underbody. The final coat of paint is then applied, the staging removed, and for the first time, the fine lines of the vessel become apparent. Anchor chain and anchors are shipped just before launching. The total weight of the 3 anchors is 54,000 pounds. The port and starboard anchors weighing slightly less than the bow anchor. Each anchor is held by nearly a half mile of 3 3/8 chain. The links are painted a different color at regular intervals to denote the amount released. Note that the final red color indicates the end is near. Lifting of a vessel from a submerged shipway reduces much of the work and practically eliminates the anxiety and thrill accompanying a sliding launching. There is, however, considerable removal work to be done below the waterline. During the construction period, the ship was supported by keel blocks, cribbing, and shores throughout her entire length. Now, much of this material must be removed. The 790 shores are knocked out one by one. The majority of the support aft, which extends above the baseline, must be removed, leaving the ship sitting on the keel blocks and side cribbing, which must all be anchored securely to the shipway floor. The gate to the shipway, as well as the flooding openings, must be inspected and cleared of any silt which may have been deposited. Soundings must be taken and the area off the shipway dredged. All of this work is completed the day before launching. The painting is touched up, gangways are removed, and all hose and cable feeding the ship are disconnected. On the afternoon before the launching, water is admitted to the shipway to a depth of 21 feet without floating the vessel, so that the underwater compartments can be inspected and closed up. On June 23rd, 1951, the United States is floated, and a preliminary inclining experiment held to determine her stability. Since it's advisable to move the ship into the stream at slack water, the time of the launching is governed by the current in the river. Crowds gather in the intense summer heat for the ceremony, speeches, and music to make this gala occasion one to be well remembered. As the final warning whistle blasts, the vessel starts to move slowly out of the shipway, and the sponsor, Mrs. Tom Connolly, wife of the distinguished senator from Texas, smashes the bottle of champagne right across the bow of the ship. I christen thee, United States. Upon the crack of the bottle, accompanied by whistles and the waving of flags, the vessel is pulled out of the shipway, stopping after a short distance so that tugs may be secured to guide her stern as she enters the stream. Slowly, she moved down the river to the outfitting pier, where nearly a year will be required to complete her for delivery. In conjunction with the design and outfitting of the accommodation spaces, sample staterooms are built and fully equipped for each of the 3 classes of rooms. These are made up to settle not only the type of construction, but also the proper location of all the fittings, plumbing, and lighting fixtures, and the selection of furniture and interior decorations. This is the first-class sample room. Each item is carefully checked to make sure that it conforms to the specifications and meets the approval of the owners before proceeding with the actual work on the vessel. Here is one of the shower stalls, completed and ready for use. Usually, stalls are erected on the ship, piece by piece, but on the United States, they were built and assembled completely in the shop. The installation of a single unit is a far more economical procedure. Built entirely of aluminum, they're rust-proof and considerably lighter than the ordinary shower stall, composed of steel bulkheads and tile floor. The sides of the stall are flanged from a single sheet of 1/8 inch aluminum, while the floor is made of diamond-checked, non-skid aluminum plate. The remaining parts are clamped in a jig and welded by one of the several approved processes. The process used here is classed as semi-automatic, in that the electrode is fed automatically through the handle of the gun, at a speed dependent upon the thickness of the material and the size of the wire. The arc is formed by the electrode and is enveloped in an inert gas, such as helium or argon, to prevent oxidation. Welds are ground smooth, trim and part of the plumbing fixtures added, and after the addition of the structural connections, the stalls are stored until the ship is ready for them. About 600 shower stalls are furnished for passenger or officers' quarters having private baths. It took skilled men in over 75 trades to build the United States. The schedule on which she was constructed resulted in an average of 2,500 men during the last 18 months. Nearly 5,000 individual workmen had a hand in her construction. This is some of the 10 miles of ductwork needed to distribute the mechanical supply and exhaust ventilation. The air conditioning supply alone requires over 300,000 cubic feet per minute. Although steel ducts were generally used below the bulkhead deck, 90% of the ducts are aluminum. All of them developed in the shop from detailed plans. Wherever practicable, trunks and ducts are concealed. They're insulated to prevent sweating as well as heat loss. This insulation is vapor sealed on all cold air supply ducts. The air conditioning plant, composed of 8 centrifugal compressors and their associated auxiliaries, feeds 62 individual systems and has a capacity of 1,800 tons of refrigeration. Here you will see some of the forming operations necessary to make the thousands of corner posts and boundary supports for the Marinite paneling. Marinite is a hard asbestos base material, which has replaced to a great extent wooden bulkheads and ceilings. The extensive use of Marinite and aluminum, together with fire-retardant paint, makes the United States the most nearly fireproof vessel ever built. With the exception of the passengers' belongings and, of course, the fuel oil, the vessel is practically devoid of combustible materials. Formed pieces, assembled into H sections, are tack welded together, forming a rigid column for use where 2 panels butt together. Aluminum clad material is used for paneling in the first and cabin class spaces. The tourist class spaces and crew quarters are finished with a polished surface material without the cladding. Over 75 different shapes are required to suit the various thicknesses and types of joints used in construction. Switches and outlets can be mounted on the face of the metal strip. The square hole in the center serves a very useful purpose for running the light and interior communication wiring. After completion of the piping, wiring, and ventilation, the bulkheads and ceilings are ready to be installed. The bulkhead paneling includes several different weights and thicknesses. In general, below B deck, the material is 7/8 standard weight, while above, both light and extra lightweight Marinite is used to further reduce the topside weight of the vessel. Ceilings in the staterooms and quarters are of 3/16 marine veneer and are stripped with steel to meet Coast Guard requirements. In passageways and other spaces where acoustical ceilings are not fitted, the marine veneer is secured with screws instead of stripping. Acoustical ceilings, which are both moisture-proof and fireproof, are fitted in all large public spaces. Where aluminum decks occur over them, they're protected against fire by 1 inch of insulating material mounted on expanded metal just above the framing. This marine-type acoustical ceiling has a density only 1/3 of that customarily used. It was developed specially for use on the United States. The electrical cable and wiring must be run between the supply points and the outlets before the ceiling or paneling can be installed. Switch panels are so located as to feed power to the miles of light, communication, and control wiring. Electrical equipment of every description is situated over a total deck area of about 500,000 square feet. Lighting in general is of 3 types: direct incandescent in the staterooms, fluorescent cornice lighting in the passageways, and indirect cove lighting of the incandescent type in all public spaces. Distribution lighting panels, as well as other power and control panels, are fed from the 3 primary stations located in different parts of the vessel. This is a primary station which receives its power from the main distribution boards in the engine and boiler rooms. 2 of the primary stations are also connected to the emergency generator switchboards, so that emergency light and power will always be available for operating the safety equipment. The main switchboards distributing alternating current to the entire ship are of the dead front type. All current supplied is AC, but in such instances as the cargo winches, where DC is required for a fine degree of control, motor generator sets are used to convert the AC to direct current. Switchboards are built up around a framework of aluminum shapes and plates and are designed in accordance with current naval practice, except where modified for protection devices. Drip pans are fitted to prevent moisture and other foreign matter from coming in contact with electrical equipment. This is the rear side of one of the boards. The red bus bars made of copper are bolted together. The joints are silver-plated for good electrical conductivity. Here you see how simply and safely damaged or faulty switches on the face of the dead front panel may be replaced without cutting off the main source of power to the switchboard. Sections of the panel are removable or, in some cases, hinged to permit access for inspection or maintenance of the equipment, which is located on sub-panels. The boards with terminals marked are completely wired in the shop, checked out, and installed on the ship as single units. The problem of handling material at the outfitting pier is much greater than that of handling structural material at the shipway, where most of the lifts are landed in their final location. Here there are only 2 25-ton cranes to handle the tons of small equipment and packaged material, most of which has to be landed on deck or unloaded at side ports and then manhandled to its assigned location within the ship. The majority of the furniture for the United States is built by manufacturers to the owner's specifications and is received ready to install. However, a few items are made at the shipyard. The crew lockers are among these. All of the parts are formed in the sheet metal shop. The frame forming the front of the locker is assembled complete with doors. The catch and the lock operating gear have been jigged and spot welded in place. Before the final assembly, the individual parts are given a priming coat of paint in a specially ventilated paint room. Drying time is reduced by the use of ovens and the penetrating heat supplied by infrared lamps. It takes about an hour to assemble a locker, complete with all of the miscellaneous hardware. The parts are secured with ordinary nuts and bolts, which are set up tight with a pneumatic wrench. 1 locker is furnished for each member of the crew. The completed lockers, after thorough inspection, are given a final coat of paint inside and out. In this unusual piece of electrical apparatus, samples of all types of paint are tested for their fire retardant qualities. The sample is heated to about 2300 degrees Fahrenheit as current is passed through the metal strip. Notice how the paint bursts into flame as the heat increases. This first sample is the ordinary type of oil paint. Watch the 2 small flames which appear at each side and then continue to burn. This shows that ordinary paint will burn at the lower temperatures occurring at the edges of the specimen. Every type of paint used on the interior of the United States is given a rigid test and proven satisfactory. Now compare the first sample with this one, which has been coated with fire retardant paint. No flame is visible at the sides. It will not intensify or propagate a fire. Even the heated portion does not burn. It merely seems to disintegrate and then falls off. The construction of the crew berths is another production item which was undertaken by the shipyard. Such items are not customarily yard-built, depending to a great extent upon the workload in the shops. The entire framework is of aluminum, which characterizes not only the superstructure of the vessel, but many of the fittings and much of the decorative work, where weight saving is of prime importance. This is a standard pipe-bending machine, fitted with numerous stops and jigs to uniformly make the 16-odd bends required to turn out the 4 individual pieces that form both the upper and lower frames. Machines of this type are used for cold bending pipe up to 14 inches in diameter. Here the frames, separated by pre-cut lengths of pipe, are clamped in a jig so the entire unit can be welded together. Although riveting was used extensively on the superstructure of the ship, aluminum welding is used on other types of work where strength is not a major requirement. This is the heliarc welding process, in which the arc is formed by a tungsten electrode surrounded by an inert gas, while the weld metal is fed manually. Nearly 700 berths are required for members of the crew. When made up, they compare favorably with those of first-class quarters of a few years ago. In place of the customary caulked wood decking, all of the exposed decks on the United States are covered with a composition material. The decks are first cleaned and then sanded to remove any trace of foreign material. Covering is spread on the bare steel or aluminum decks in several coats, building up to a total thickness of 3/16 of an inch. Actually, there are 9 coats. The first 7, including the subcoat for leveling, and the 7th, the bond coat, are troweled on. The remaining 2 coats, the final bond coat and the sealer, are sprayed. Sloping metal ladders have replaced all wooden ladders, aluminum being used above decks and steel below. Assembly of the stringers and treads is easily accomplished, since the holes for the rivets were drilled in a jig. The simple riveting operation takes only a few seconds because the rivets are so shaped that the automatic gun pulls them tight, sets up the ferrule, and cuts off the surplus material in one operation. Rivets such as these have many applications, but are used here principally for assembling. Most of the strength is obtained by welding the treads at the 4 points of support. Although railings forward of the house front are of the standard steel type, all other exterior railings are of aluminum. The hollow aluminum cap rail, used in place of the customary teak rail, is a special extruded section which was first fitted to the vessel and then removed, anodized, and reinstalled. Cargo on the United States is handled by the customary booms and winches. Self-supported king posts are installed forward between number 1 and number 2 hatches, and similarly aft between number 4 and number 5. Topping winches are fitted to the king posts. All weather deck hatch covers are steel and of the quick operating type. The forward covers are hinged at one end and in the middle, the other end being fitted with rollers on each side. The track at the hinged end is inclined in such a manner that the cover, upon release, will close by gravity, even with a 30-knot wind blowing against it. Tween deck covers, except at E-deck forward, are the steel pontoon type, hinged and mechanically operated to swing outboard. In a raised position, the underside of the cover becomes flush with the hatch opening, making a nearly continuous flat surface on the inside of the trunk. The safety of the passengers on the United States is guarded much like that of a naval vessel. A damage control room, manned 24 hours a day, contains all of the safety controls, alarms, and means of communication for the passenger's safety, be it fire or collision. In the event of an accident, the attending officer has complete facilities for closing the necessary watertight and fire screen doors to subdivide the ship into small compartments. Emergency squads can then investigate the trouble, while the alarm and emergency announcing systems are available if necessary. Life-saving equipment exceeds the requirements of both the U.S. Coast Guard and the International Convention for the Safety of Life at Sea. Sufficient capacity is provided in the aluminum lifeboats to accommodate all persons on board. 2 of the boats are motor-driven, while the others are manually operated by mechanical means geared to the propeller. Not only are the boats built of aluminum, but all of the fittings are either aluminum or other non-combustible material, even to the hollow aluminum oars which will float. About 2 months before the vessel is to be delivered, a dock trial is held. With the ship adequately moored to the pier, the individual shafts are rotated at a fraction of their designed 39,500 horsepower, to be sure that all of the main and auxiliary machinery is in good working order before taking her on the trial runs. As the United States nears completion, her interiors and public spaces are painted out, decks are carpeted, and decorations are put up. Contrast this lived-in appearance with the various construction stages over the past 2.5 years. This is the first-class dining room. The 4 galleys serving the 2,000 passengers and nearly 1,100 members comprising the officers and crew contain every time-saving device, from electric potato peelers to power-operated garbage disposal ports. The first-class galley here serves both the first and cabin-class passengers. These are the electronic ranges capable of cooking steaks by means of penetrating high-frequency heat in a matter of seconds. The galley proper is located on the center line, while at the sides are the vegetable rooms, bake shops, butcher shops, and various pantries. Here is the swimming pool, surrounded by the artistically decorated beach area. The decorative signal flags say, "Come on in, the water's fine." Adjacent are the showers, dressing, and therapy rooms. Many new materials were used on the interiors. Fabrics, floor coverings, and drapes were selected not only for color and texture, but also for their moisture and fireproof qualities. Luxurious suites are well appointed to blend with a general theme. This is the Duck Suite. Little work remains to be done when the United States is in operating condition and ready for her sea trials. The official trials of the United States were conducted at sea about 100 miles off the Virginia Capes in 1,200 fathoms of water. The speed of the vessel was determined by means of radist, a relatively new electronic navigation system. In this system, the speed is calculated from the time and the known distance between the ship and a free-floating buoy containing part of the electronic equipment. The chief advantage of using such a system is the ability to standardize a ship in deep water without having to resort to the trial course at either Rockland, Maine or Guantanamo, Cuba, neither of which is ideal for a vessel the size of the United States. These are 2 of the radist buoys on the deck of the Coast Guard tender Conifer, which placed the buoys and stood by them during the trial runs. Only 1 buoy is necessary to obtain the data, but 2 were used, operating on different frequencies in case of severe radio interference. The buoys are about 42 feet high, of which 20 feet are underwater. They were built with a large base to house the electronic apparatus, while the upper section was made of pipe so as to be reasonably steady in a rough sea and drift as little as possible. Being free-floating, they move with any current which may exist, and thus give the speed of the ship through the water, instead of relative to the ground as obtained on a measured mile course. The launching of the buoys from the Conifer was a hazardous operation and a tribute to the personnel of the U.S. Coast Guard and their successful accomplishment of the job. The buoys were spotted from the United States with radio direction finders. Smoke bombs were set off to visually aid in locating the buoys, but were extinguished by the heavy seas, making their use ineffective. This is the master station on the United States. The cabinets on each side contain a complete transmitter, receiver, and phase meter apparatus. Like the buoys, this equipment is also in duplicate. In the center is the time mechanism, while the two chart recorders, which show both the distance traveled and the elapsed time, are located in the foreground. The vessel made alternate runs with and against the wind to cancel any effects of wind or drift. The runs were approximately 5 miles long, one end of the run being 2 miles from the buoy and the other end 7 miles. At 22 knots, notice the absence of any bow wave, such as is customarily seen in pictures of destroyers at high speed. This is, of course, the result of the shape of the forebody. The spray at the extreme bow results from the stem being rounded. In some of the pictures, you'll notice an apparent pitching of the United States, but this is due purely to the movement of the camera on the conifer, which was experiencing very rough weather at the time. With the completion of the trials, the United States heads back to the shipyard, having been the first ship to conduct a complete, accurate standardization trial without depending on a measured mile. This magnificent ship, built by Newport News, was delivered to her owners on June 20th, 1952. By establishing new speed records for crossing the Atlantic in both directions, she has proven already that she's worthy of the great country's name she bears. Our best wishes go with her. May she serve as a proud reminder to our nation that American-built ships help to keep all America strong.